Good afternoon. Good afternoon. Welcome again to our virtual pre-lab lecture. Today we are going to look at a simple lab on introduction to acid and bases, and I believe you have covered the concept of acid and bases in Introduction to Chemistry, and in Chem1 as well as in this course if you are taking the lecture part of it this semester. As far as this experiment is concerned, you need to be in a position to calculate the pH from the simulation. You'll be able to, or you should be able to calculate the pH of a solution and determine the hydroxide concentration and the hydronium concentration of few substances we will look at. We're not going to, or I will not require you to do the calculation for all the substances given in the simulation. Let's first of all look at an overview of what an acid is and what a base is. Probably maybe you know how to define, or you only know one version of the definition of an acid or a base. Allow me to share my screen here so that I show you the whiteboard and what you need to know as far as the acid and bases are concerned. You should, when we look at the acids, all right, or acids, or an acid basically, you should have three versions. There is Arrhenius, all right, Arrhenius definition of an acid. There is Bronsted, Lowry. These are the two, and these two came up with that definition of an acid. And then there is Lewis, all right, Lewis definition of an acid. These are the three, there are three versions of the definition of an acid, and you should be able to distinguish and differentiate. Otherwise, given multiple choice exam, you may use another definition trying to answer a question for another one. This is the first person who came up with the definition of an acid, and he simply proposed or defined an acid as any substance, all right, any substance that produce, all right, or produce hydrogen ion in H2O. When dissolved in H2O, you have to state that it produces hydrogen ion, or simply this is just proton donor. I didn't mean to do that. Proton donor. This has an example of this is e.g. Example of that is HCl, nitric acid, all right, sulfuric acid. They all have hydrogen in their chemical formulas. This is, or these are Arrhenius acids. When you look at this Bronsted, they define or redefine the definition of an acid as this is simply right here. This shouldn't be here, but this is for Bronsted Lowry. This is just proton donor, and the difference is the pace. When you look at the pace, Lowry divine, Bronsted Lowry definition of a pace is totally different from Arrhenius. You're gonna look at that. And then here, Lewis definition is electron, and you have to say this, electron what? Electron pair, acceptor. That means it is accepting what? It's accepting electron. Example for Bronsted could be, you know, HCl, it donates a proton, all right? Nitric acid, it donates a proton. It's the same thing. Constant fluorine definition of an acid we can also use for what? We can also use for arenas. And this could be proton acceptor. It could be hydrogen ion. It can accept 2 electrons. It can accept 2 electrons pairs from any Lewis pairs. Now, when we look at the pairs right here, all right, according to Arrhenius and Bronsted, Lowry, and then there is the Lewis here, you should be able to draw a parallel between the 3 definitions of an acid, according to Arrhenius, according to Bronsted, and according to Lowry. When you also look at the base, these are any substance that produce what? That produce OH when dissolved in H2O. For example, sodium hydroxide, this is Arrhenius space. It has OH in the chemical formula. KOH, all right, it has a chemical formula OH. Calcium hydroxide, OH in their chemical formula. Anything that produce hydroxide, all right, you know this is polyatomic ion called hydroxide. Now, Bronsted Lowry definition of a base, here it doesn't have to have OH. This is simply defined as any substance that generate OH. All right. For example, this is Arrhenius space, but it does not have OH in its chemical formula, but it generates OH by accepting hydrogen from water molecule. All right. If we dissolve ammonia in water molecule, 1 hydrogen from H2O will form ammonium hydroxide, and this will just be produced in H2O. So that's the difference between Arrhenius and Bronsted Lowry definition of a base. When we look at the Lewis, all right, this is Lewis right here. Any substance that donates electron pair. So this is, excuse me, electron what? Electron pair donor. It donates electron. For this, you should draw the Lewis dot structure for a compound in order to see the lone pairs of electron. This is a Lewis what? This is a Lewis space. It has 2 pairs of electron to be donated. H2O also can serve as the Lewis what? As the Lewis pairs, because it has 2 pairs. All right, these are the pairs to be shared with any other substance or any other compounds which needs 2 lone pairs of electrons. So that's how you differentiate between the 3. You should be able to differentiate between the 3 versions of the definition of an acid over base. And of course, when we talk about an acid and a substance, it is with reference to hydroxide concentration and hydronium concentration. Sometimes we interchange these hydronium and hydroxide. Any substance which has, any substance which has higher concentration of hydroxide compared to hydronium, it's a base. Any substance that high concentration of hydronium than hydroxide, we say that, or we consider that as an acid. Apart from using that, we also use the pH. All right, pH is pH is a scale used to determine whether whether a solution is an acid or a pace, and it ranges from 0 to 14, where the middle one is considered a neutral solution, a pH of 7, neutral. Anything greater than 7 going towards 14, we say that this is basic. And anything below 7, we say this is acid. And of course, you know, the concept of changing the litmus paper to red and changing litmus paper to red and red to blue is also another criteria of classifying a solution as an acid and as a base. So given the pH value, the lower it is, the more acidic the solution is. The higher the pH value, the more basic the solution it is. All right, I've talked about the pH and how do we determine the pH of a solution? pH, if you know the hydroxide concentration or hydronium concentration, negative log of hydronium concentration give you the pH value. pOH is given by the negative log of what? Negative log of hydroxide concentration. It's not always true that you know, you'll be given a solution which is acidic and you are asked to find the pH of a solution. You may be given an acid and you are given to find the pOH, or you are given a base and you are asked to find the pH of that base solution. In that case, you'll have to utilize this equation: pH plus pOH equals to what? Equals to 1 times 10 raised to, 1 times pH equals, not that, equals to 14.00. When you add that, this is an equation you should be able to use to find the pH of a basic solution. For example, if you are given 0.25 molar NaOH and you are asked to find the pH, for example, this is a basic solution. NaOH is a basic solution. Negative log of this value will give you pOH. Then how are you going to find the pH? Is by making use of the equation in the box to find the pH of the solution. So that one also is used to find the pH. And there is this relationship between the hydroxide concentration and hydronium concentration at room temperature. That means at 25 degrees Celsius, 1.0, the product of hydronium concentration, hydroxide concentration equals to 1.0 times 10 raised to negative 14 at 25 degrees Celsius or at room temperature. You have to know this relationship as well so that you use to find the pH. Going back to this equation, these two equations right here, the way it works for significant figures, and I know, you know, when you do the quiz, I don't want you to make a mistake of, you know, just going by the values. If you look at a worked example on how to find the pH, let's see, it's a pH. There was one example on how to find the pH. This one, I want to point out the pH and the hydroxide concentration. Yes, let's start here. Look on the lab manual, or rather the handout where my cursor key is. If you are given a solution, look at this. If a solution has a pH of 5, 2. This has 3 significant figures. And from what you know, you should always express your final answer with the correct number of significant figures. That's what we learned. But when it comes to pH, concept of the pH and calculation, the way you treat the significant figures is slightly different from what you already know. Look at this. I know if you are given the pH, all right, negative log of this value, you'll have expected to, you will have expected this to have 3 significant figures. But the final answer is given with 2 significant figures, all right? The number of places of decimal corresponds to the significant figures in the pH and vice versa. So the what determines the significant figures in the final answer, given the concentration, the molarity, you have to look at the place of decimal. Look at this place of decimal here is 2 places of decimal, and the final answer should have 2 significant figures, 2 significant figures. The reason why I'm bringing this one is I'll give you multiple choice quiz on this lab, and somebody will just take the calculator and key in and say, all right, you know, this is what I see in my calculator, and you know, I pick choice A or choice B, and you'll get it wrong, and you will not have time to fix it. You'll only have one trial. So remember, if you're looking for the pH, the significant figures corresponds to places of decimal in your final answer. So remember that, okay? So it's not a coincidence that we only have 2 here. It has to do with 2. So if I had like this, 2.5, 3, 1, for example, and then my final answer will be with 3 significant figures, 3.0, 2, using what we have in the, all right, using what we have in the lab manual pH. So that's how you look at the what? You look at the significant figures. Places of decimal, significant figures. Now, given the hydroxide concept, or given the pH, and you are looking for hydroxide, pH is given, or hydroxide concentration rather, is given by the 10 or antilog of the pOH value. And hydroxide is given by what? Given by antilog of the pH value. In both cases, you got to look at the significant figures as well, because of the 2 places, very significant. Any question on the pH? Any question? So this is the equation you're gonna use in today's lab to find the, this is the equation you're gonna use, this one right here. This is the equation you can use to find the relationship between hydroxide and all right, hydroxide and pH and the pOH. Hydroxide, hydronium is equals to 10 raised to what? 1.0 times 10 raised to negative 14 at 25 degrees Celsius. This is the equation you will use to find. Look at this. This is what you will need in completing the data table. Let me see if that is. You look at this. On the data sheet, you will find the hydroxide concentration and hydronium concentration. To get the hydronium concentration, we have to know the pH. So you got to find the pH, you got to find the hydronium concentration, you got to find the hydronium and hydroxide concentration. using this equation. I will show you, I'll show you one example on how you will complete this table. All right, I'll show you the simulation, all right, simulation before and after the dilution. Here is the simulation you will go to. And I noticed that, you know, Adobe sometimes doesn't work well playing off. I want you to go to the modules. I noticed that, you know, if you try to play straight from the link, it might not really work. It may require you to download or update the Adobe, which might ask you to buy like $99. So what I did is I embed the link on Canvas, which will play, but it's not gonna be straightforward. It's got to be, you have to click a couple of steps. So let's see the simulation on today's lab, number 8, right here. You see the simulation? If you click that, this is what you'll see. You may not see this, but sometimes you may see that a warning. You'll see a warning here, and then the word simulation. Please click that simulation here and it will play. It will load for your simulation on finding the pH. This is where you will put for water, and this is the pH Pro. And this is where you will pick the solution you want to find the pH. And right here, it is, this is where you need to say, if I can look for example, maybe Patrick, I said like, or I can do, let me just do this. I can do that, all right. This is where you press to release whatever you are testing the pH. The direction called for using 0.1 ml of each substance. In this case, if I'm using 0.1, all right, doesn't really matter whether you start by just bringing the pH probe in there or you put it later on. And then the volume here will change to 0.1. You see, it's changing to 0.1. That's what I need to, oh, I overshoot it. So what I'll do is just drain that and it's come back to 0. So you gotta be careful until you end up with 0.1. If you look at, let's see, yeah, it wasn't all the way. You see that? It should be inside. This is the pH of just undiluted. That is what you will put it in the, right here, before dilution. You see this? Before dilution, the pH of, you know, whatever you have here. I don't have the spit. I'm just using the spit as an example. You know, you gotta do the same thing for each substance right here. What is the volume? You're gonna write down what is the pH. In that case, I will use, or I'll write 7.7 pH is, for that example, it was what? pH equals to 7.40. So hydronium concentration from the pH. Hydronium concentration from the pH is given by antilog 10 raised to negative pH value, which is 10 raised to negative what? 7.40. Let me ask you this. How many significant figures should I have in my final answer? Somebody real quick tell me, and then I'm gonna walk. Let me grab my calculator. My calculator was just right here. 3 significant figures? No. It is good that you just pointed because I don't want you to make. Thank you, Cynthia. it is three significant figures. Let me show you, look, so that we don't make the same mistake. And it's good that you just point out that, because if it was a quiz, you will click A and then you will be like, what happened? I used the right equation. Let me back up to the pH. Let's go back to the example right here and we do the anatomy. If the pH of a solution, you see the pH has three significant figures, 2 places of decimal. So 10 raised to the pH value. Look at my whiteboard, 10 raised to negative pH value. That's what I'm doing exactly right here. 10 raised to. So it will be 2 significant figures because of the 2 places of decimal. It's kind of like weird when it comes to pH concept. That's how it is in the pH. In the world of pH, in the world of acid and bases and pH, you have to pay attention to the significant. It's not the way we know. This is the only exception in the significant figures. I know you learn this and like it's different. But yeah, Cynthia, you're right. That is, we should have 2 significant figures. So I'm gonna give you a quiz, and somebody who is not here or somebody who not watch the recording might make the same or the same mistake. So if I say that 10 raised to negative 7.40, and I see my calculator giving me 3.98107. This is more than what I need actually. This is more than what I need. And using the rounding off, this will be 2 significant, which is 4.0 times 10 raised to negative 8 molar. So that's what I'll do in, that's what I'll do for what? That's what I'll do for P4. You see this? P4, P4 dilution. And then to get the hydroxide concentration, if I know the hydronium concentration, use this equation, the relationship between hydroxide and hydronium. You divide by, okay? Hydroxide concentration in that case will be 1 times 10 raised to negative 14 over 4.0 times 10 raised to negative 8. That's how you find the hydroxide concentration, 1 negative 14 divided by what? Divided by 4.0 to negative 8. And I see it is 2.5. 2.5 times 10 raised to negative 7. So that's what I'll do before I do the dilution. And then here is after the dilution. The direction called for, you know, adding 0.9 ml. You'll read that. You see, this is 0.1. And you got to be careful with the, you know, you got to be careful with the addition. Don't assume and say that it doesn't really matter. You know, what I'll do is not reset, but you'll have to add water, not this tab right here. This is for the reagent or substance. So I'll just, the further you push this, the more H2O. This is for dilution. You may have like a small, you know, it's just gonna rise slowly. You see how it's gonna rise? You want to end up at 1. If you overshoot, you have to start over again. Because I've done this, you know, I've done this and I know the value. Look at the pH value, it's changing, all right? It's changing. This, I don't want to overshoot. So maybe just go slowly until I add 0.9 to make it 1 liter, all right? So I'm just, oh, I didn't get it. Oh, you see, this is what happened all the time to me. This is what happened all the time. So I'm gonna dump that. All right. And then add 0.1. Yeah, and then you have to be careful on how you add water, how you dilute the solution. All right, if you don't, if you overshoot it, you got to start over again because it's gonna affect your pH value. Yes, that is where you want. And this is the pH after the dilution. You'll do the same thing and fill the data table right here. What is the pH? You write down, you calculate the hydronium concentration, and you go in there. So that's what you do. Now, Cynthia, you have a question here. If we show you a work for one of the substance, do we still need to show the work for the rest of the items? Well, you still have to do the calculation because the pH value will change. And if the pH value change, there is no way. Maybe the pH, you know how you end up with this. If you know the pH value for here, how will you end up with that? You have to subtract, right? The pH. I would want you to show the work for all what we see here. Not all. If you look at Cynthia, I know you're wondering about all those if you have looked at the simulation. I didn't pick all of them. Look at this. We have 1, 2, 3, 4, 5, 6, 7. Only 7. But on the simulation, you have a lot. You know, you have a lot. You don't need to do all this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You don't need to do 12. You don't need to do 12. All you have to do is the only one you have on what? You have on the data sheet right here. So we don't do all the substances on the simulation. I hope that answers your question. But in case of trying to find hydroxide, unless you know shows the setup here is pretty straightforward. Cynthia, I hope that answers your question. And once you have done with that, there is a follow-up question here. You want to look at that and answer the question below the data table. You can attach any extra sheet of paper to show your workout, all right, to show your workout. All you'll be working with is the only substances you have here, all right? That's all what you need to worry about. Other than that, that's all I want you to do. That's all what I want you to do for this lab, introduction to acid and bases. I will post a post lab for this lab and as well as the quiz. Please continue working on the previous quizzes I posted. What I'll try to do is make it available as we go so that you can work. Remember, today is July 1st, so technically we have 3 weeks. Last day of this course is July 31st, July 31st. Other than that, the class is dismissed. If there is no other question, I will see you next Wednesday. In case you have a question, please feel free to mail me and I'll respond. Thank you for tuning in today. I'll see you next week. I'll now stop sharing my screen. Have a wonderful afternoon. Bye.